So in this last video about DC motors, we're going to take a look at something called an H-bridge, which is also commonly referred to as a transistor array. So in the previous videos, we looked at how you can use a transistor to control high current, high voltage loads with motors, and but they would only spin in one direction, even if we could vary the speed. But a lot of times you want to spin a motor in two directions because it has that capability. And so that's where this thing called an H-bridge comes into play. So on the it's an IC. You know, it's a 16 pin chip. The particular one, there are many different ones out there. The particular one that I'm using is called an L293D. The pinout for these things is kind of standardized, but so I'll walk you through what these things do. We'll take a look at some wiring, and then I'll give you a demo of how you can adjust the speed and the direction of a motor, of a DC motor. Most of these are wired up so that you could actually control two motors. So that's helpful if you're doing something like building a robot and you want to have it pivot or swivel, something along those lines. Uh, I just have one here, so it'll have to do. Uh, on this, if we look at the chip and remember that when you're looking at a chip, the part with an indented U at the top is going to be the top of the chip, and we count down pins starting in the top left-hand corner, and then it follows that sort of U shape. So 1 through 8, and then on the other side 9 through 16 in the opposite direction. So pin 1 is the enable pin. This basically turns it on. This also is a pin that we can use for PWMing, so it will help us determine the speed of the motor. Uh, Pin 8 is the motor power. So this is where you would plug in your external power supply. Uh, Pin 16 is the power from the microcontroller, or the thing that you're going to be using to control it. So you still need to control this off of your microcontroller, even though it's got motor control down here. Same way that you would have to, have a separate power for uh, motor versus uh, just a microcontroller if you're using a transistor. And then there's a couple pins that you need to pull to ground. So in this case, it's pins 4 and 5. Both these will go to ground. And then on here, you've got pins 2 and 7 go to the microcontroller. And then pins 3 and 6 connect to the motor. So the way that this works is that there's if you pull the pins one pin high and one pin low, the motor will spin in one direction. If you flip-flop that or invert it so that this opposite pin is high and the first pin is low, then the motor will spin in the opposite direction. If both of the pins on the microcontroller go high, the motor stops. If both pins on the microcontroller go low, the motor stops. So you can see here this illustration does a nice job. If both of these are open, then there's nothing connecting the motor. If both of them are closed, then the motor is in a brake position. But remember, the way in which the motor spins is determined by the flow of the current across the terminals. So if we flip that, and that's what we're doing here, we can get the motor to spin in opposite directions. So here's one orientation where one pin is open and the other one is closed. And so you'll see how current will flow through there, cause the motor to spin in one direction. And if you flip that, current will flow in the other direction across the motor and move it in the opposite direction. So this is the basic idea. If you really wanted to, you could take a look at the data sheet, which I'll provide a link to. There's a there's a lot inside of here. This is the chip that we're using. This is my circuit over here. The actual one, as you can see in the top right of the video, is a little bit of a snake pit, unfortunately. So this illustration hopefully will give you a slightly clearer idea of what's going on. I've got my external power supply right here. I've got common ground between that and the microcontroller. I also have the ground going into the chip. Also, I'm using my switch as an is a pull-up, input pull-up. So I don't need to connect that to power, use a pull-down resistor. I just connect one end to ground, the other end to the microcontroller. And so when I press it, I read a zero or a low instead of a high. It's just an inversion of how we normally think of switches. And then I've also got a ground going into one side of this potentiometer. The power from the motor driver goes directly into the motor power on the H-bridge. And the power from the microcontroller goes to power the chip itself. And then it also goes into my potentiometer. I've got analog pin 0 reading the value of the potentiometer, digital pin 6 reading the value off of the switch. Digital pin 3, you can see here, is my enable pin. So this is the pin that PWMs the chip to determine the speed. That's set by the value off of the potentiometer. And then pins 4 and 5 are connected to the two input terminals on the H-bridge. And so those are the two that are flip-flopped to get the motor to spin in different directions. So here, the code, uh, it's long, it's kind of long. It's not quite as complex as the wiring might seem at first. Uh, but it's because what I'm doing in here is I'm doing a little bit of a debounce thing to check for when the button is pressed to reverse direction. Um, so I've got variables in here for the motor speed, the potentiometer, the switch, the enable pin, the in and out pins, so the motor control pins, a variable for the direction for the motor, because it's going to go in both ways. It's either going to be 1 or -1. And then I've got variables to hold both the current button state as well as the button state from the last time we went through the loop. And this will help me determine when there's a falling edge off of a button press to change direction. So in the setup here, I'm setting the appropriate pins as outputs. That's the enable pin and the motor control pins. And then I'm configuring the pin that has the switch as an input pull-up. And again, this configures it so that the pin there's an internal pull-up resistor. You're familiar with the pull-down resistor that you've been using to pull a switch down to ground. So this enables an internal pull-up resistor, which means that our pin is always high until we apply ground to it. So that means that we've got a little bit less wiring on our breadboard, which is, in a tight thing like this could be helpful. You'll see that I'm actually spread this out to 2 half-size breadboards here just for ease. All of this could cram onto one, but it'd be really cramped. Inside of the loop, I'm reading the value off the analog sensor and I'm dividing it by 4. This will give me a value between 0 and 255, which will control the speed of the motor. 0 is off, and over 200, and 255 is full on. After that, I'm just writing that out to the enable pin. Now, if you wanted to, you could just turn the enable pin on or off if you didn't care about speed. But this is just a nice excuse to control the rate at which this spins. Next, what I'm doing is I'm reading the button state. So I'm reading the value off of the switch pin. And then here in this if statement, what I'm doing is I'm checking to see if the current state is different from the previous state. This will indicate that there's been a transition or a change. So this is how I know it's been pressed. So if the current state does not equal the previous state and the current state is low, which means that the button is being pressed, because I'm using this input pull-up thing, then multiply the direction variable by -1. So this means that it'll just change between 1 and -1 all the time. After that, we update the previous button state variable to the current button state. So next time through the loop, we have whatever we use this time. And then finally, what we're going to do is we're going to tell the motor which direction to spin. So if we have our pins out 1 and out 2 in one configuration, where out 1 is low and out 2 is high, the motor will spin in one direction. And if we invert that, as we see right here, if the direction variable is -1, then the motor will spin in the opposite direction. So the logic behind it is pretty straightforward. It's just the wiring can get a little bit messy, but it works really well and reliably. So I'm just going to plug this in right here, and so I'll pick up the motor, and when I turn this, we'll see it'll start to spin. There we go. And here's my button. And when I press this, I'm not sure how well it'll show up in the camera, but it'll stop and start spinning in the opposite direction. So it'll stop for just a moment. You'll probably see that. Yeah, there you go. Also, I don't think you can pick this up through the microphone, but there's a different sort of cadence in the noise that's coming out there. But if I press the button again, it flips around in the opposite direction. So I'll get it to go really fast and do this a couple times. And you'll notice sometimes that if you slow it down, we get it going pretty slow. Right, so it's slow enough that you can actually see the rotations kind of. Now, if I press this button, it's probably going to stop. And that's because it can't overcome inertia. We talked about this in the previous video, but inertially, it's once it's stopped, it tries to go in the opposite direction, but it can't. So I need to apply a little bit more current here in order to get it to actually overcome. There we go. So it'll continue spinning even if it's gone past this point where it won't start up again. That's just because it's already got the momentum to do so. But that's all you need to get a motor to spin in two different directions. The H-Bridge is also used in the next set of videos that'll come out in controlling a stepper motor, which is a sort of think of it as like a hybrid between a one of these DC motors and a servo. So that'll come up sometime in the near future.